Before we dive into the most mind-breaking story about parallel worlds, quantum computers, and the true nature of reality, please do one thing. Hit that subscribe button and give this video a like. It genuinely helps this channel keep exploring the deepest mysteries of existence with you. Now, take a breath, because what you're about to hear will change how you see every choice you've ever made. Every time you make a decision, nothing happens the way you think. You do not choose one path and reject the other. Instead, you become the version of yourself who remembers turning left, while another version of you, just as real, just as conscious, remembers turning right. And both versions, right now, are convinced that they are the only one. This is not a philosophical word game or a poetic metaphor for a clever conversation. It is a mathematical consequence of equations we trust exactly as much as we trust them when we launch satellites and build nuclear reactors. The equations of quantum mechanics do not say that the other versions disappear. They say that the other versions become separated. That is not the same thing. And that difference changes absolutely everything. To understand why physicists are so certain that reality branches around you right now, we have to go back to the experiment that started this dizzying conversation and that remains the most disturbing demonstration of how the universe violates common sense. The double-slit experiment. Imagine a tennis ball and a wall with two open holes. If you throw the ball, it will go through either the left or the right hole. Elementary logic. If you throw 1,000 balls, behind the wall you will see two piles, one opposite each hole. That is how objects behave in the world we live in. But in 1927, when scientists performed the same experiment with electrons, something impossible happened. They fired electrons at a barrier with two tiny slits, expecting to see two spots. Instead, they saw a complex pattern of many vertical bands, an interference pattern. Exactly the kind you get when water waves pass through two slits, spread out, overlap, and collide, creating a series of peaks and troughs. But the scientists were firing electrons one at a time. There was no second electron for the first one to collide with. How could a single particle create a wave pattern? The only mathematical explanation is this: the individual electron did not choose a path. It actually split into a ghost wave, passed through the left slit and the right slit simultaneously, interfered with itself on the other side, and then struck the screen. This experiment proves that at its deepest level, matter is not solid. It is a wave of possibilities. But then it got even stranger. When the scientists suspected something was wrong and placed a detector at the slits to secretly watch which hole the electron went through, the behavior stopped. The moment it was observed, the electron stopped acting like a wave and returned to the behavior of a solid tennis ball, passing through only one slit. It was as if the particle knew it was being watched and decided to hide its true nature. This forces a question that has haunted physicists ever since. Does the universe look solid only because you are looking at it? And if you stopped looking, would the chair you are sitting on dissolve back into a wave of infinite possibilities? For decades, physicists tried to sweep this problem under the rug. In the 1920s, the legendary physicist Niels Bohr and his colleagues developed the so-called Copenhagen interpretation. They argued that when you measure a particle, you force it to choose. The wave of possibilities collapses into a single reality, and all other possibilities simply dissolve into thin air. That was a convenient explanation. It saved our intuitive picture of the world. It told us that although atoms behave strangely, the world we live in is safe and singular. But there was one problem. The mathematics of quantum mechanics never described this collapse. The equations did not say that the other possibilities disappear. They said that they become separated. In 1957, a young graduate student at Princeton University named Hugh Everett III decided to take the mathematics literally. He looked at the equation and asked a simple, dangerous question. What if the wave never collapses? What if the electron does not choose one slit or the other but actually passes through both, and the universe splits into two to accommodate both outcomes? Everett argued that when you measure a particle, the universe branches into two separate, non-communicating layers of reality. In one layer, you see the electron going left. In another, an identical version of you sees the electron going right. That was the birth of the many worlds interpretation. It suggests that reality is like a radio signal constantly splitting into different frequencies. The fact that you are tuned to one frequency does not mean the others have stopped broadcasting. Everett showed that collapse was a myth we invented to feel better about living in a single world. But if he was right, nature never destroys information. Every time a quantum event has several possible outcomes, all of them happen. The most common objection to this idea is that it only applies to the subatomic world. You can look at your hands and say you are not an electron. But this objection collapses when you follow the chain reaction of observation. Imagine a single radioactive atom that has a 50% chance of decaying and releasing a particle and a 50% chance of remaining stable. That is the famous Schrödinger's cat setup. The atom exists in a superposition, both decayed and not decayed. But the atom is not isolated. It interacts with a detector device. According to the laws of physics, when a quantum particle interacts with a larger system, that system becomes entangled with it. The detector enters a superposition, having detected radiation and having detected nothing. Then the signal reaches a vial of poison. The vial enters the superposition, broken and intact. Then the poison reaches the cat. The cat enters a superposition, alive and dead. And finally, you open the box. Light from the cat hits your retina, travels along the optic nerve, and excites neurons in your brain. There is no physical barrier that stops the spread of this splitting. Superposition infects everything it touches. The moment you look at the result, you become part of the equation. Your brain physically enters two different states. In one branch of reality, your neurons record a live cat. In another, a dead cat. Both versions of you are equally real, and both feel that they are the only one. This is the mechanism of the multiverse. It is not about traveling to distant dimensions. It is about constant branching here and now. Every time a neuron in your brain fires, a process driven by the movement of ions and electrons, the universe accommodates the alternative. This means that your consciousness is constantly splitting through the space of probabilities. If you are listening to this text right now, there is a version of you that got distracted and switched off 5 seconds ago. That version is as real as you, but you will never be able to speak to it again. And here is the question that follows, which sounds simple but is incredibly deep. If you are constantly splitting, who is the real you? Are you the trunk of the tree? Or are you just one individual leaf unaware of the forest around it? This is where skepticism hits a wall when you look at the technology that sits right now in Google's and IBM's laboratories. Quantum computers. These machines are not simply faster versions of the laptop on your desk. They operate on a fundamentally different logic that practically forces us to accept the existence of parallel realities. An ordinary computer processes information in bits, tiny switches that can be either on or off, representing 0 or 1. It creates one linear line of computation. A quantum computer uses qubits. A qubit is a particle, like an electron, held in a magnetic trap. Because of superposition, a qubit can represent 0 and 1 simultaneously. If you connect enough such qubits, the machine can perform millions of calculations at once, not one after another. The pioneer of quantum computing, Oxford physicist David Deutsch, posed a challenge that skeptics have never satisfactorily answered. He asked us to imagine a quantum computer factoring a number with more digits than there are atoms in the observable universe. When the computer returns the correct answer, it has performed more individual calculations than there are particles in the cosmos to keep track of them. Where exactly were those calculations performed? If the visible universe does not have enough resources to hold the scratch paper for that math, the computer must be using resources from somewhere else. Deutsch argues that the only logical explanation is that the computer distributes the workload across parallel versions of itself in other timelines, collaborates with its shadow copies. When we run a quantum algorithm, we are effectively outsourcing our homework to the multiverse and then collecting the answer. If parallel worlds do not exist, how can the machine perform a task that requires more computing power than exists in all of our reality? The fact that these computers work is the strongest physical evidence that the walls of our reality are porous. But if this happens at the microscopic scale of quantum choices and electrons, does it stop there? We tend to think that the strangeness of quantum mechanics is limited to the tiny world of atoms, while the big world of stars and galaxies follows a simpler set of rules. But what if the entire universe is just one bubble in a much larger sea? What if the Big Bang was not the beginning of everything, but just a small pop in an endless firework display? To understand where the other worlds hide, we have to move from the atom to the edge of the cosmos. If space is infinite, can you truly be unique? In 1981, late one evening at the Stanford Linear Accelerator Center, a young physicist named Alan Guth was trying to solve the main problem with the Big Bang theory. The problem was that the universe was too smooth. Everywhere scientists looked, the temperature of the cosmos was almost identical. This should not be possible unless the entire universe was once in contact to equalize heat and then expanded faster than the speed of light to its current size. Gauss proposed a radical idea called inflation. He suggested that, in the first fraction of a second, gravity actually reversed. Instead of pulling things together, it repelled everything with violent explosive force. This repulsive gravity stretched the fabric of spacetime from the size of a proton to the size of a grapefruit in less than a billionth of a trillionth of a second. The theory was brilliant, and observations have since confirmed it. But there was a catch that Gauss and later physicist André Linde discovered. The mathematics of inflation suggests that once this rapid expansion starts, it is very difficult to stop. In our local patch of the universe, inflation stopped 13 billion years ago. But the theory predicts that inflation does not stop everywhere at the same time. It continues in other parts of the fabric, stretching space further and further forever. This is called eternal inflation. It paints a picture of the universe constantly expanding like rising bread. While our little corner of the bread stopped rising and formed a crust, our universe, the rest of the dough continues to expand, creating new bubbles of stability. The best way to visualize this dizzying structure is to imagine a giant pot of boiling water. The water represents the high-energy, rapidly expanding space of the inflationary multiverse. As it boils, tiny bubbles of steam form inside it. Inside those bubbles, the water has stopped boiling. Our entire observable universe is just one of those tiny steam bubbles. We float inside a pocket of stability where the violent expansion stopped, allowing stars and planets to form. But outside the walls of our bubble, the water is still boiling. The space between bubbles expands so fast, faster than the speed of light, that the bubbles are forever separated from each other. That is why we have never seen these other worlds. We are physically separated from them not by a wall, but by the sheer speed of expanding space between us. If other bubbles exist, are they like ours, or are they strange hostile wastelands? The theory suggests that when a bubble forms, it captures a specific set of physical laws inside, like a roll of the dice. In our bubble, the roll gave us the electron mass and the strength of gravity that allows stars to shine. But in a neighboring bubble, the dice could have fallen differently. Maybe gravity is repulsive there, maybe light does not exist, maybe atoms cannot bind together. We may live in a rare Goldilocks bubble, surrounded by an ocean of dead, dark universes where life is physically impossible. But if the dice are thrown an infinite number of times, the perfect combination must repeat. String theory, developed by pioneers like Edward Witten and Leonard Susskind, suggests that the fundamental particles of matter are not tiny points but vibrating strands of energy. Just as a violin string can produce different musical notes depending on how it vibrates, these cosmic strings produce different particles depending on their vibration frequency. But here is the catch. The vibration of a string is determined by the shape of the space in which it wiggles. String theory predicts that our universe has extra dimensions, 6 or 7 of them, curled up into tiny invisible knots called calibi, Yau manifolds. The shape of these knots dictates the music of the strings and therefore the laws of physics. The problem is that the equations of string theory allow an almost infinite number of different shapes for these knots. Specifically, there are at least 10 to the power of 500 possible solutions, a 1 with 500 zeros. That enormous collection of possibilities is called the landscape. Each solution represents a permissible stable universe with its own unique set of physical laws. This leads to one of the most unsettling observations in all of science, the anthropic principle. When we look at the constants of nature, the mass of the proton, the strength of gravity, the charge of the electron, we find that they are fine-tuned to an impossible degree of precision. If the force of gravity were just a few percent stronger, stars would burn out in a million years, leaving no time for evolution. If it were a few percent weaker, stars and galaxies would never have formed at all. It seems we have won a cosmic lottery with odds so low they are practically zero. For a long time, this fine-tuning was used as an argument for a great designer. It seemed too perfect to be coincidence. But the multiverse offers a solution that requires no design, only statistics. Imagine a hotel with an infinite number of rooms. In most rooms, there is no air conditioning, no water, and they are filled with poisonous gas. Only one room in a billion has a comfortable bed and fresh air. If you wake up in a comfortable room, should you be surprised? No, you are in a comfortable room because if you were in a poisonous one, you would not be alive to ask questions. That is the essence of the anthropic principle. We observe a universe compatible with life not because the universe loves us, but because we could not observe a universe that is not. Now the most concrete question. If eternal inflation creates infinite space, and if that space is infinite, can you be unique? MIT physicist Max Tegmark did the math. He calculated that you would need to travel a distance of roughly 10 to the power of 10 to the 29 meters. To be clear, that is a double exponential. It is not a 1 with 29 zeros, it is a 1 with 10 billion 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 zeros. If you tried to write that number on paper, the paper would have to be wider than the entire observable universe to hold the zeros. That distance is so vast that it makes the distance to the edge of our galaxy look like a single step. But in the context of an infinite multiverse, that distance is nothing. At that exact distance, statistically, there exists a volume of space that looks identical to ours. There is a sun the same age as ours to the nanosecond. There is a planet orbiting it with the same geography as Earth, the same continents, the same oceans. And on that planet, inside a room that looks exactly like yours, there is a person who has your DNA, your memories, your scars. They remember your first day of school. They remember the taste of the breakfast you ate this morning. Up to this exact second, their life has been a perfect mirror reflection of yours. Here is what is particularly interesting about this level I multiverse, as Tegmark calls it. The copy does not have to remain perfect. It is a separate physical entity. Its future is not written. What happens when the copy makes a move that you do not? Imagine looking through a telescope that could see that far. You focus the lens on that distant Earth. Zoom in on your city. Find the window of your doppelganger's house. You watch them sitting in a chair, just like you. But then something changes. In your reality, you decide to keep listening to this text. But in their reality, a neuron in their brain fires slightly differently because of thermal noise. They decide they are thirsty. Get up, go to the kitchen, pour a glass of water. In that fraction of a second, the symmetry is broken. You are no longer identical. You have branched into two different variants of one person. This means that the infinite library of space contains not only exact copies, it contains every possible version of you. If you go further out, you will find a version of you who wore a red shirt this morning instead of blue. Go further and you find a version of you who took that job offer in another city 5 years ago. Go even further and you find a version of you who became a professional musician instead of an accountant. In our single bubble, we are haunted by the limits of time and choice. We can live only one life. But in the infinite space of the level I multiverse, you are living all of them simultaneously. There is a world where you avoided every mistake you ever made. There is a world where you realized every dream you ever had. Those people are not strangers. They are you, separated only by space. But here is what makes this whole picture especially gripping. The collider in the laboratory is not just speculative equipment. Quantum computers running right now in Google's and IBM's laboratories are real machines giving real answers that require real resources. And if Deutsch is right about where those resources come from, then we are already using parallel realities as computational infrastructure. Not in the future, right now. We are already sending calculations into the multiverse and getting answers back. And yet most people think these are just faster computers. The cold spot in the constellation Eridanus is a detail that, when examined, speaks of a specific physical trace that a neighboring universe might have left when it collided with ours. In 2004, NASA researchers were analyzing a new high-resolution map from the WMAP satellite when they discovered something that should not have been there. In the southern hemisphere of the sky, in the direction of Eridanus, there was a blue spot, not just an ordinary blue fluctuation, but a giant, deep blue hole. This region, known today as the CMB cold spot, is a patch of sky about 5 degrees across 1 billion light-years in diameter that is significantly colder than the surrounding universe. Specifically, about 70 microkelvins colder than average. Statistically, the chance of a spot this size and this cold appearing randomly in a standard universe is about 1 in 50. Theoretical physicist Laura Mersini-Houghton proposed a radical solution that fits the data with terrifying accuracy. She suggested that the cold spot is not a void. It is a bruise. Her hypothesis is based on the bubble multiverse picture. Imagine our universe is a soap bubble floating in a room full of other bubbles. If our bubble came too close to another and they touched, the collision would not necessarily destroy them. Instead, it would push the walls of our universe inward. That impact would release a massive shockwave of gravity and energy, pushing matter away from the point of contact. As the universes bounced off each other and expanded, that point of contact would stretch out, leaving a giant circular region of lower density and temperature. It would look exactly like the cold spot we see today. When the Planck satellite data came back in 2013, the cold spot did not disappear, it became sharper. Planck confirmed that the temperature anomaly was statistically significant, reaching a level of about 3 sigma. That means there is a 99.7% probability that this object is real and not random noise. And the shape of the spot matched simulations of bubble collisions. If the cold spot really is a scar from a collision, it proves that our universe is not an isolated system. It proves that there is an environment beyond our space-time, a higher dimensional space where universes float and collide like ships in a storm. This turns the multiverse from a mathematical possibility into physical geography. We have a neighbor, we touched it, and if we touched it once, billions of years ago, who says we are not colliding with someone right now? What if the collision is happening not at the edge of the universe, but right here under our noses? That brings us to the concept of the brain multiverse. It suggests that a parallel version of you could be sitting on your chair right now, reading a different screen, and you would never know they were there. But if they are so close, why do we not bump into them? Why do we not see them? The answer lies in why gravity is so ridiculously weak. Electromagnetism is roughly 10 to the 40th power times stronger than gravity, a 1 with 40 zeros. That is roughly the difference between the weight of a single virus and the weight of the entire visible universe. In 1999, two physicists, Lisa Randall and Raman Sundram, proposed a solution that changed everything. They suggested that gravity is not actually weak. It is just as strong as the other forces. But unlike the other forces, it leaks. Imagine you are watering a garden with a hose, but the pressure is terrible. You check the hose and find it is full of holes, spraying water sideways before it reaches the nozzle. Randall and Sundram proposed that our universe is a leaking hose, and the water leaking out is gravity. But where does it leak to? Into extra dimensions. The graviton, the particle that carries gravity, is a closed string, a loop. It has no free ends to attach to our brain. That means gravity is free to drift from our universe into the bulk. That is why gravity feels so weak to us. We feel only a tiny fraction of the gravity that remains on our slice of the universe, while the rest leaks into extra dimensions. Here is what follows from this, and it truly changes everything. If gravity can leave our universe and travel into the bulk, can it also travel from the bulk to us? And more importantly, is there anything else floating in that bath? If we accept the brain world hypothesis, our view of reality changes from a single bubble to a giant loaf of sliced bread. Our universe is just one slice, but there could be another slice or another brain, floating right next to us, separated by only a millimeter of bulk space. That is a fourth spatial dimension, a direction you cannot point to, but that physically exists. And dark matter, that mysterious invisible substance that makes up 85% of the mass of the universe and that we have been searching for in detectors for decades, might not be matter in our universe at all. It could be the gravitational shadow of ordinary matter living on a parallel brain next door. We could be sharing space with an entire shadow civilization that is less than an atom's width away from us in the fourth dimension. We are alone on our sheet of paper, but the stack is full. Here is what right now is the most accurate description of our position. Physics does not say that parallel worlds are possible. Physics says that parallel worlds are a direct consequence of the equations we already accept as true, the very equations that power the quantum computers in Google and IBM. The choice you are making right now, to continue listening or to stop, does not eliminate the alternative. It simply makes you the version of yourself who remembers this choice, while another version of you, equally real, equally conscious, equally convinced of its uniqueness, lives out the other outcome right now. That does not mean your decisions do not matter. It means they matter for the specific version of you that you are. And the only version of you you will ever know is the one sitting here right now listening to this. The mirror universe and why it is not a metaphor but a concrete physical structure predicted by mathematics. This is what, when examined, speaks of a fundamental symmetry built into the very foundations of physical equations. In 1914, Julian Barber and his colleagues proposed a model called the Janus point theory, after the ancient Roman god Janus, who had two faces, one looking forward and one looking back. Their mathematics shows that when a system of particles collapses into a dense cluster and then expands, it naturally splits into two separate streams moving in opposite directions from the center. In our pocket of the universe, time flows forward as the universe expands, entropy increases, galaxies form, and we age. But on the other side of the Janus point, there is another universe. In that universe, time also flows away from the center, but relative to us it moves backward. This effectively creates two arrows of time pointing in opposite directions from a common beginning. The reason we do not see antimatter is not because it is not there. It has gone into the other pocket of the universe. Symmetry is restored not by finding the missing half here, but by realizing that here is only half the picture. The universe is a butterfly with two wings, and we have spent all of history looking at only one. The mirror universe is not a chaotic wasteland. The laws of physics there are exactly the same as ours. There is gravity, electromagnetism, light. There are likely its own stars, its own planets, and possibly its own observers. But the relationship between our world and theirs is literally mind-flipping. From their point of view, their time flows forward. They remember their past, which is closer to the Big Bang, and move toward their future, which is farther away. They break eggs and make omelets. But if you could look at their universe through a magic telescope from ours, everything would look reversed. You would see them aging backward. You would see their universe contracting from a dark void into a bright singularity. You would see broken cups jumping off the floor and sealing themselves. To them, we are the ones moving backward. We are the mirror world. This model implies that the Big Bang was not a unique explosion but a gateway, continuously pumping existence into two diverging streams. It is the ultimate realization of Newton's symmetry. For every action, there is an equal and opposite reaction. For our entire history of time, there is an equal and opposite anti-history. Does that other universe contain a version of you living in reverse? Probably not. The two worlds split 13.8 billion years ago. The chaotic mixing of atoms means that the specific details would be different. It is not a perfect mirror of events, but a mirror of structure. It is a world where the sun rises in the west, made of antihydrogen and antihelium. But the most poignant thing is that we can never visit it. To get there, we would have to travel backward in time through the crushing density of the Big Bang and come out the other side. We are physically cut off from the other wing of the butterfly. We are swept away by the very flow of time that gives us life. The block universe and why it means that the past never goes away. This is a concept that, when examined, speaks of a static, frozen nature of all of space-time simultaneously. In 1915, Albert Einstein united space and time into a single four-dimensional object called space-time. In this model, time is not a process but a dimension, just like length, width, and height. Imagine a loaf of bread. You can slice the bread into individual slices. Each slice represents a moment in time, a snapshot of the universe at a particular instant. But the loaf itself exists all at once. The beginning of the loaf, the Big Bang, and the end of the loaf are physically connected and equally real. This is the block universe theory. In the block universe, nothing actually happens. The entire history of the cosmos, from the Big Bang to the final fading, is a static, frozen structure. It is a crystal of events. Your birth, your first kiss, and your last day are all inscribed in this crystal at different coordinates. They exist simultaneously. The reason you feel you are moving through time is that your consciousness crawls along the timeline like a needle on a record. That is what it means if the block universe is real. Nothing is ever truly lost. The moments of joy you experienced in the past have not disappeared. They are still there, fixed in the amber of space-time, existing forever at their specific coordinates. The universe does not delete its history. It just builds new structure. This turns grief on its head. The person you loved who died is physically present in the crystal of space-time at the coordinates that correspond to the moments you shared. This is not a comforting metaphor. It is a literal consequence of general relativity, accepted as a fundamental description of reality. The arrow of time and why it is a condition, not a law. This is one of the deepest open questions in physics, which when examined speaks of a specific contradiction between fundamental equations and our subjective experience. You can stand still in space. You can choose to sit in your chair or walk to the door. You have freedom of movement in 3 dimensions. but you cannot stand still in time. You are dragged forward at an inexorable speed of 1 second per second, toward a future you cannot see, away from a past you cannot return to. Why does this flow exist? If we view the universe as a giant block of space-time, then past, present, and future exist simultaneously. Why do we experience only the now? Here is the answer physics gives, and it is unexpected. The fundamental laws of motion, Schrödinger's equations, Maxwell's equations, Newton's laws, do not care about entropy. They are time-symmetric. That means if you film 2 billiard balls colliding and play the film backward, the backward film perfectly obeys the laws of physics. At the microscopic level, there is no arrow of time. An atom does not know the difference between past and future. So why does the building decay if the building blocks of reality are time-neutral? This suggests that the arrow of time is not a law, but a condition. It exists because the universe began in a specific state of incredibly low entropy after the Big Bang. We are surfing on a wave of increasing disorder. The reason you can tell yesterday from tomorrow is that tomorrow is more disordered than yesterday. The universe began in a state of incredible order and has been sliding toward chaos ever since. Cosmological natural selection is a theory that, when examined, speaks of the laws of physics themselves not being carved in stone, but subject to the same evolutionary pressures that shape birds and bees. Theoretical physicist Lee Smolin proposed applying Darwinian logic to the cosmic genes themselves. In standard physics, the electron has a certain mass because it just does. It is a brute fact. But in biology, nothing is just because. A giraffe has a long neck for a reason, because its short-necked ancestors died out. Smolin suggests applying this logic to stars. Could it be that our universe has the specific laws it has because it evolved them? That we live in the fittest universe, the one that won the survival competition? Smolin's argument begins with a problem known as the Goldilocks enigma. When physicists measure the fundamental numbers that define our reality, they find something troubling. The universe seems to be balanced on a knife's edge. The strength of dark energy pushing the universe apart is a tiny, specific number. If that number were even slightly larger, the universe would expand so fast that atoms would be torn apart before they could form stars. If it were slightly smaller, the universe would collapse back into a black hole milliseconds after the Big Bang. The same is true for the strong nuclear force that binds protons together in the atomic nucleus. If it were 2% stronger, hydrogen would instantly fuse into helium, and there would be no water or sun-like stars. If it were 2% weaker, nuclei would fall apart, and the periodic table would be empty. There are about 20 such numbers, and each falls into the incredibly narrow range necessary for life to exist. The chances of this happening by accident are effectively zero. Smolin proposed a third explanation for the fine-tuning beyond miracle and survivor's bias. The universe is not lucky. It is adapted. Just as a polar bear is adapted to cold not by chance, but through inheritance, our universe is adapted to create life because it inherited those traits from a parent. But if the universe has a parent, how is it born and where is the egg? Smolin looked at the resemblance between the world of biology and the world of physics and realized they are practically mirror images. In biology, there is a genotype and a phenotype. The genotype is the genetic code, the DNA instructions telling cells how to build the body. The phenotype is the body itself. Smolin proposed that the universe follows the same structure. The body is the physical universe we see around us. Galaxies, vacuum, light. What is the DNA? Smolin suggested that the universe's genes are the fundamental constants of nature. The mass of the proton, the strength of the weak nuclear interaction, the speed of light. These are not random numbers. They are the genetic code that defines the shape and behavior of the universe. Just as a small change in DNA can turn a wolf into a chihuahua, a small change in these constants can turn a universe filled with stars into a universe filled with diffuse gas. For evolution to work, you need a reproduction mechanism. Where exactly do universes reproduce? The answer requires looking at the most violent and mysterious objects in the sky: black holes. For a long time, we viewed them as the universe's trash cans. A star runs out of fuel, collapses under its own weight, and tears the fabric of space-time where nothing, not even light, can escape. We saw them as endpoints, places where information goes to be erased. But general relativity offers a different picture. When a massive star collapses, it crushes a huge amount of matter into a tiny point called a singularity. At that point, density becomes infinite, and the laws of physics as we know them break down. But the mathematics suggests that spacetime does not simply end at the singularity. Instead, it bounces.
Imagine a rubber sheet.
If you press a heavy ball into it, it stretches into a deep funnel. If you press hard enough, the funnel might pinch off from the bottom and expand outward into a new bubble on the other side. Smolin suggests that this is exactly what happens. The singularity is not a dead end. It is a seed. The matter and energy falling into a black hole in our universe do not disappear. They travel through an Einstein-Rosen bridge, a wormhole, and burst out the other side, triggering a big bang in a completely new, separate region of spacetime. From our perspective, a black hole is a dark, heavy sphere. But from the perspective of an observer inside the black hole, it looks like the beginning of time, a new universe rapidly expanding from a hot, dense point. This means that every black hole in our galaxy is technically a baby universe in formation. It grows, expands, and develops its own structure, completely cut off from us by the event horizon. The event horizon is the eggshell. The key part of Smolin's theory is what happens to the genes at birth. When the singularity bounces, quantum mechanics introduces an element of randomness. Extreme energy fluctuations cause the constants of physics to shift slightly. This is a cosmic mutation. The daughter universe might have a proton 1% heavier than the parent, or a slightly stronger gravity. This small change creates the pressure of natural selection. Some universes will have bad genes. Maybe a mutation makes gravity too weak for stars to form. In that universe, gas just floats forever. No stars, no black holes, no descendants. That universe is sterile, an evolutionary dead end. Other universes will have good genes. Their laws of physics are perfectly tuned to turn gas clouds into massive stars that then collapse into black holes. A universe with such genes is highly fertile. Over billions of generations, the population of the multiverse will become completely dominated by these fertile universes. That is why the laws of our universe are so perfect for making stars. Our universe is the product of a long lineage of master breeders. We are not the first iteration of reality. We are the result of eons of cosmic optimization. But here is the most stunning twist. If the universe's goal is simply to produce black holes, where do we fit in? Are we just accidental tourists at a factory that was not built for us? Smolin suggested something astonishing. The universe is not fine-tuned for life. It is fine-tuned for black holes. It just so happens that the conditions necessary to create a black hole are almost identical to the conditions necessary to create life. To make a black hole, you need massive stars. To form massive stars from gas clouds, you need a way to cool the gas so it can condense. It turns out that the most efficient coolant in space is carbon monoxide. You need heavy elements, carbon and oxygen, to act as chemical radiators, helping stars condense. A fertile universe must produce vast amounts of carbon and oxygen. It must allow complex chemistry. Those are exactly the same ingredients needed to create a human. We are not the universe's goal. We are a chemical byproduct of the cosmos's reproductive system. We are like moss growing on the bark of a tree. The tree exists to drop acorns and grow new trees, not to support the moss. But the moss thrives anyway because the conditions on the bark are suitable. But there is one wild card. What if biology is not just a side effect but part of the mechanism itself? If we follow the logic of evolution to its limit, we have to ask, does nature ever stop innovating? In biological evolution, simple cells eventually united into complex animals because complex animals were better at surviving. Could the same happen with universes? Right now, the universe produces black holes through a blunt, brute force method, gravity-crushing stars. This is dirty and inefficient. Most of the star's matter is blown away in the explosion. Only a tiny core becomes a black hole. But what if the universe evolved a more efficient way to reproduce? What if it evolved a tool that could take matter and deliberately compress it into black holes with precision? That tool would look very much like intelligent life. We already collide particles at high energies. Theoreticians have suggested that a sufficiently advanced civilization could produce artificial black holes for energy or computation. If the universe evolves intelligent life, and that life goes on to create billions of artificial black holes, that universe gains a massive reproductive advantage. Maybe we are not just moss. Maybe we are the reproductive cells of the cosmos. Max Tegmark's mathematical universe is the final and most radical level of the multiverse. which when examined speaks of the very distinction between the physical world and the world of mathematics being a lie. We usually think of mathematics as a tool we invented to describe the world, a language. We use numbers to count apples, but numbers are not apples. But what if we are wrong? What if numbers are the apples? What if the universe is not described by mathematics, but literally made of mathematics? When we ask, what is a chair made of? We say wood. What is wood made of? Molecules. Molecules from atoms, atoms from subatomic particles, protons from quarks. But what are quarks made of? If we look at the standard model of particle physics, a quark is described as an excitation in a quantum field. But what is a field? A field is a mathematical value assigned to every point in space. See what just happened? We started with a solid chair and ended with a list of numbers. We chased the substance of reality all the way down, and the substance vanished. We discovered that the foundation of the universe is not solid material, but a set of mathematical properties. An electron is not a tiny ball. It is a collection of values: mass, charge, spin. If you remove those numbers, nothing remains. There is no electronness underneath the math. The electron is the mathematics. Tegmark argues that our physical reality is a mathematical structure. Think of a video game. When you play, you see trees, cars, and people. But what is the game really? If you look at the hard drive, there are no trees inside. There is only code, sequences of zeros and ones. The physicality of the game world is an emergent property of information processing. Tegmark suggests our universe is the same, but without a computer. In mathematics, complex structures exist simply because they are logically consistent. You do not need a computer to make the number pi real. Pi exists independently of whether you calculate it. The ratio of a circle's circumference to its diameter is a timeless truth. It existed before the Big Bang and will exist after the stars go out. If mathematical truths exist independently of time and space, and if our universe is just a very complex mathematical structure, then our universe exists necessarily and eternally. It does not need a creator to start it. It exists in the same sense that a triangle exists. It is a property of logic itself. Here is where this literally blows the doors off the multiverse. The structure that describes our universe, with our specific speed of light and our specific gravity, is just one of an infinite number of possible mathematical structures. Logic admits other structures. It admits universes with other numbers, other geometries, other rules. If the mathematics for those universes is consistent, do they exist too? The answer, according to the mathematical universe hypothesis, is an unequivocal yes. This leads to the broadest possible definition of reality. Every mathematical structure that does not contain a logical contradiction exists physically. The only thing that does not exist in the multiverse is the impossible. You cannot have a universe where 1 + 1 = 3, because that is a contradiction. But everything else, please. This removes the question, why? Why these laws? Why this gravity? The answer, because there is no why. We are simply observing one specific address in an infinite district of mathematics. We are exploring one specific fractal in an infinite set. We are here because this structure supports self-aware substructures called humans. Here is what right now is the most honest and most accurate summary of everything we have considered, from Schrödinger's cat and the double-slit experiment, to Google's quantum computers and the Eridanus cold spot, to Barber's mirror universe, to Smolin's cosmological evolution, to Tegmark's mathematical universe. All these ideas, with different methods and different starting points, arrive at the same structural conclusion. Reality is significantly larger than what you can see from your observation point. What you perceive as a single world is either one branch of a constantly splitting quantum tree, or one bubble in a boiling ocean of inflation, or one slice in a stack of brain worlds, or one address in an infinite library of mathematical structures. None of these models is an exotic invention just for beauty. Each is a direct consequence of the physics we already trust. The physics that explains why quantum computers work, why galaxies rotate as they do, and why the cosmic microwave background has the anomaly that Planck confirmed in 2013. The only thing preventing us from fully accepting this is not the data. The data is there. What prevents it is that accepting it requires radically rethinking what reality is and what you are. Decoherence, and why it specifically explains why we do not see quantum splitting in everyday life. This is the concrete physical mechanism that, when examined, speaks of parallel branches of reality not just existing in theory, but also explaining why we do not notice them. The main objection to the many worlds interpretation has always been, if the universe is constantly splitting, why do we not see it? Why does the chair you are sitting on look like one chair and not a blurry cloud of millions of chairs? The answer is decoherence, the process by which a quantum superposition loses its interference properties when interacting with the environment. Every atom in your body is continuously interacting with billions of other atoms in the air, in the light, and in the floor beneath your feet. Each of those interactions carries information about the atom into the environment. And this scattering of information over a huge number of environmental degrees of freedom makes the quantum superposition practically unobservable at the macroscopic level.
Decoherence happens incredibly fast.
For an object the size of a dust particle, it takes about 10 to the minus something seconds. So fast that it is impossible to observe superposition without immediately destroying it by the very act of observation. That is why quantum computers need to be cooled to temperatures near absolute zero, about minus 273 degrees Celsius. At that temperature, the thermal fluctuations that cause decoherence are suppressed enough that the qubits can hold superposition long enough to perform calculations. This is not some metaphysical complexity. It is a mundane engineering problem. Keeping a quantum system sufficiently isolated is the reason quantum computers are so hard to build. And overcoming decoherence is the main technical obstacle to full-scale quantum computing. The fact that we have already built machines that partially overcome decoherence, and that they work exactly as the many worlds interpretation predicts, is not a coincidence. Entanglement as a fundamental connection between branches of reality. This is what, when examined, speaks of a specific quantum phenomenon that, properly understood, ceases to be a mystery and becomes a natural consequence of the universe not destroying information. Quantum entanglement is a state in which two or more particles are described by a single quantum wave function. Measuring the state of one particle instantly determines the state of the other, regardless of the distance between them. Einstein called this spooky action at a distance and never accepted it, believing there must be a hidden local variable explaining the results. In 1964, John Bell derived mathematical inequalities that made it possible to experimentally test the existence of such hidden variables. All subsequent experiments, including the Nobel Prize-winning work of Alain Aspect, who received the Nobel Prize in Physics in 2022, showed violations of Bell's inequalities. No hidden local variables exist. Entanglement is real and non-local. In the context of the many worlds interpretation, entanglement gets an elegant explanation that the Copenhagen interpretation lacks. When two particles become entangled, their quantum wave functions become inseparable components of a single shared wave function. When you measure one of them, you are not transmitting information instantly across space. Instead, the branches of reality in which you get different results become orthogonal. They stop interfering with each other. Your branch picks one outcome, while another branch where you got a different outcome continues to exist. Entanglement is not action at a distance, it is correlation between branches. And that is exactly what makes entanglement so useful for quantum computing. It allows correlations between qubits that exist in superposition of many states simultaneously. The uncertainty principle and why it is not a technical limitation of measurement but a fundamental property of reality. This is a detail that, when examined, speaks of uncertainty being built into the very fabric of existence. In 1927, Werner Heisenberg formulated his uncertainty principle. The more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. This is not a matter of imperfect instruments. It does not mean that if we had a fine enough device we could measure both simultaneously. Uncertainty is fundamental. A particle does not have a simultaneously precise position and precise momentum. These quantities are not defined simultaneously by nature itself. That is the key to understanding why superposition is not just our ignorance. When a novice physicist hears that an electron is in superposition, they often think it simply means we do not know which state it is in, like a coin that has already landed heads or tails but is covered by a hand. We just have not looked. But the double-slit experiment completely refutes this interpretation. If it were just ignorance, an electron that passed through a specific slit could not create an interference pattern. Interference requires that the electron went through both slits simultaneously, not in our imagination, but in physical reality. Superposition is not our ignorance. It is the real physical state in which the object exists before measurement. The measurement problem and its connection to consciousness. This is one of the most philosophically troubling aspects of quantum mechanics, which when examined speaks of the specific question of the role of the observer in physical reality. When physicists say measurement causes the wave function to collapse, what exactly do they mean by measurement? What counts as measurement? Is interaction with an air atom enough, or does a conscious observer need to be involved? This is where quantum mechanics steps into territory that seems almost metaphysical. Some physicists, including Eugene Wigner, suggested that consciousness plays a special role in the collapse of the wave function, that conscious observation causes definiteness. This has caused huge controversy. Within the many worlds interpretation, this problem is elegantly solved. Consciousness is not a special physical process standing above quantum mechanics. A conscious observer is a quantum system like any other. When it interacts with a quantum object in superposition, it itself enters a superposition. One branch contains the observer seeing one result, another branch contains the observer seeing the other. Both branches contain fully functioning consciousness, each convinced it is the only one. This solution is beautiful, but it creates its own puzzle. What does it mean to be an observer in superposition? What is subjective experience in a world where you are constantly splitting? If there are a billion branches right now containing versions of you, which one is the real you? The answer the many worlds interpretation gives is that they are all equally real, and each is convinced it is the only one. That is what makes this approach to physics simultaneously the most mathematically economical and the most psychologically provocative of all. It does not violate the equations, it takes them literally. And taking them literally leads to a picture of the world that makes everything around us significantly stranger than we are used to thinking. The quantum Zeno effect and how observation literally slows down quantum evolution. This is a concrete laboratory-confirmed phenomenon that, when examined, speaks of the connection between observation and quantum behavior being not a philosophical abstraction but a measurable physical reality. The quantum Zeno effect is named after the ancient Greek philosopher Zeno of Elea, known for his paradox of Achilles and the tortoise. The essence of the effect is this: if you observe an unstable quantum object frequently enough, you can prevent it from decaying. This was experimentally confirmed in 1986 by Wayne Itano and colleagues at the U.S. National Institute of Standards and Technology. They observed beryllium atoms, continuously irradiating them with laser pulses. The more often they interrupted the evolution of the atomic system with acts of measurement, the slower the atoms transitioned from one quantum state to another. Frequent enough observations could completely freeze quantum evolution. This is not a metaphor, not an approximate result. It is a precisely reproducible laboratory result following strictly from the mathematics of quantum mechanics. The act of observation literally changes the speed of physical evolution of the system. And there is an inverse effect, the quantum anti-Zeno effect, where sufficiently frequent observations can accelerate quantum transitions. Both effects are practical tools being considered for use in quantum computing. They demonstrate that observation in quantum mechanics is not passive registration. It is a physical interaction that changes the behavior of the system. And if observation changes behavior, then the question of what an observer is and what its status is in physical reality ceases to be a philosophical decoration. It becomes a central question of physics. The quantum tunneling effect and how it literally allows particles to pass through barriers that classical physics says are insurmountable. This is what, when examined, speaks of the limits of reality that we think of as absolute being merely statistical. Imagine a ball rolling toward a hill. In classical physics, if the ball does not have enough energy to get over the top, it stops and rolls back. No exceptions. But in quantum mechanics, a particle described by a wave function has a non-zero probability of being found on the other side of a barrier even if its energy is formally insufficient to overcome it. That is quantum tunneling, and it is not a theoretical curiosity. It is literally the basis of our technological civilization. Without quantum tunneling, no semiconductor transistor would work. Flash drives would not work. The scanning tunneling microscope that lets us see individual atoms would not exist. And most astonishingly, without quantum tunneling, the sun would not shine. Nuclear fusion in the sun's core happens at temperatures insufficient to overcome the classical Coulomb barrier between protons. Protons literally tunnel through that barrier, and that is what makes stars possible. What does this tell us about the nature of reality? It tells us that prohibitions in the physical world are not absolute, they are probabilistic. A barrier is not insurmountable. It is just extremely unlikely to be surmounted at large scales. Given enough scale, in an infinite universe with infinite time, any event that is not forbidden by absolute logical contradiction will eventually occur. That is the physical basis for the everything that is not forbidden is mandatory principle that Tegmark discusses. What actually happens when you make a decision? This is a question that, when examined, speaks of the specific neurochemistry and quantum mechanics intersecting in your brain right at this moment. The brain is a quantum system. This is not a metaphor or an exaggeration. It is a literal physical fact, because the brain is made of atoms and molecules that obey quantum equations. Every time a neuron fires, it is triggered by the movement of ions through membranes, through molecular channels whose behavior is described by quantum mechanics. There is a controversial hypothesis, quantum consciousness, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, which suggests that quantum computations in the microtubules of neurons play a key role in conscious experience. That hypothesis remains highly debated, and most neuroscientists do not accept it. But even without invoking that specific hypothesis, the very fact that the brain is a quantum system means that, in principle, its states can be superpositional. However, classical neuroscientists and quantum physicists generally agree that at the scale of neural activity, which is a thermal mesoscopic phenomenon, decoherence happens so fast that quantum superpositions practically do not affect the deterministic outcome of neural firing. This means that, in a practical sense, the decisions you make are determined by the prior physical state of your brain. But that is precisely part of the many worlds interpretation. You do not need to appeal to a special role of the brain to create splittings. Splittings happen constantly at the quantum level throughout the universe. Your brain is simply part of that continuous process. Borges's library and why the Argentine writer, who wrote it in 1983, created the most accurate metaphor for the Level 4 multiverse. This is a cultural story that, when examined, speaks of human imagination sometimes anticipating physics in grasping the structure of reality. In his story, Borges imagined a library containing every possible book that could be written, every combination of letters in a book of a certain size. Most books are pure nonsense, but in this library there also exists a book containing the exact history of your life, down to your last thought, and a book with your life history but one typo, and a book with the history of what would have happened if you had turned right instead of left on that particular day, and a book with the true history of humanity's future. The library does not exist in our physical space. It is an abstract conceptual space of all possibilities. That is exactly Tegmark's mathematical universe. Only instead of books, there are mathematical structures, and instead of being abstract possibilities, all consistent structures are physically real. This turns the question of creativity on its head. When a writer creates a world, he does not invent it. He discovers a coordinate in the infinite library that was already there. When a scientist derives a mathematical theorem, he does not create it. He discovers it. Pi was not invented by Archimedes. Pi existed before Archimedes, before the universe, before time, because it is a logical consequence of the definition of a circle. In Tegmark's mathematical universe, all of this existence is not a metaphor. It is physical reality. The truth that Borges wrote as literary fiction turned out to be a physical model of the multiverse that Tegmark developed as a serious scientific hypothesis 30 years later. Mathematics and literature met at a single point. Here is what right now is the most important practical consequence of everything we have considered. Not for cosmology, not for physics, but for understanding your own life. If the many worlds interpretation is correct, if every time a neuron fires slightly differently, a new branch arises, then regret for missed opportunities is philosophically meaningless. Not because missed opportunities do not exist, but because they exist in a literal sense, in other branches. The version of you that made the other choice is right now living with the consequences of that choice. It is as real as you. That is the genuine meaning of the phrase parallel worlds are real. It does not mean your decision does not matter. They completely determine who the specific branch of you is. But it means that the weight of unlived lives, the weight that most people carry in the form of the question, what if, is an illusion. What if did not destroy the possibility. What if became a specific branch that is now living in that possibility. That is what makes the physics of parallel worlds not just an intellectual exercise, but a genuinely therapeutic view of reality. Not because it is a comforting fiction, but because it is a consequence of the same mathematics that powers the most advanced computing machines humanity has ever built. Google's and IBM's quantum computers work. They give correct answers. And the only consistent explanation for where they get the computational resources for tasks that require more calculations than atoms in the universe is that they use parallel branches of reality. That is not an assumption, not poetry. It is engineering reality working in laboratories right now. The problem of identity in the multiverse and what it means for the question of who exactly is reading these words right now. This is a philosophical story that, when examined, speaks of a specific paradox that arises when the physics of many worlds confronts our intuitive sense of ourselves as a single, continuous being. You remember your childhood. You remember the breakfast you ate this morning. You have a feeling of a continuous thread of consciousness that binds all these memories into a single whole called you. But if the many worlds interpretation is correct, that thread has split countless times since your birth. Every time a neuron in your brain fired slightly differently due to quantum noise, a new branch arose. In each branch, there is a version of you with a full set of memories, convinced it is the only and continuous one. Each feels the same subjective stream of consciousness, and each is right in its branch. This leads to a strange conclusion. Identity in the multiverse is not an object, it is a pattern. Not something that continues through time as a physical object, but rather like a melody that can be played on different instruments. Each branch contains a full version of the melody, all the memories, all the personality, everything you call you, but no branch is more real than the others. That is why philosophers discussing the implications of many worlds sometimes say that personal identity in this context is indexical. It simply means this particular branch from the point of view of the observer in it. You are the branch listening to this right now. Other branches are not other people. They are other yous. But that difference itself is fundamental, because neither you nor they have access to the experience of the other branch. The no-cloning theorem and why it is a quantum law that fundamentally distinguishes the multiverse from any science fiction narrative. This is a specific mathematical result that, when examined, speaks of information in quantum physics behaving completely differently than in classical physics. In 1982, physicists William Wouters and Wojciech Zurek independently proved the so-called no-cloning theorem of quantum states. It states that it is impossible to create an identical copy of an arbitrary unknown quantum state without disturbing the original. This is a direct consequence of the linearity of quantum mechanics and the superposition principle. In the classical world, you can copy information as many times as you like without changing the original. In the quantum world, this is fundamentally impossible. That is why quantum encryption keys are theoretically absolutely secure. Any attempt to intercept a quantum signal inevitably disturbs it, and that disturbance is detectable. This is not a question of the hacker's computing power. It is a question of fundamental physics. Right now, quantum encryption networks are already operating in the world. China has launched a quantum communication network more than 2,000 kilometers long from Beijing to Shanghai. Europe is actively building a quantum internet. This is not futurology. It is real infrastructure based on the laws of quantum mechanics, the same mechanics that also predicts the splitting of reality. Every time you use quantum encryption, you are indirectly using the same fundamental principles on which the multiverse is based. Quantum teleportation and what it actually is, as opposed to science fiction. This is a story that, when examined, speaks of a real physical phenomenon that is simultaneously more impressive and more limited than how it is usually portrayed. Quantum teleportation is a real effect, experimentally confirmed starting in 1997. It allows the quantum state of a particle to be transmitted from one place to another without physically moving the particle itself. However, it does not allow matter or information to be transmitted faster than light. To complete teleportation, a classical communication channel is required. That is why quantum teleportation does not violate special relativity. What exactly is being teleported? Information about a quantum state. The original particle loses its state. This is a direct consequence of the no-cloning theorem. You cannot transmit a quantum state while preserving the original. Right now, the distance record for quantum teleportation is held by the Chinese satellite Mischius. In 2017, quantum states were successfully teleported between ground stations via satellite over a distance of about 1,200 kilometers. This is not a cabinet experiment. This is quantum physics realized in space. And all of this works because quantum entanglement, that spooky action at a distance that Einstein disliked, is a real physical resource that can be manipulated and used. The universe in which quantum teleportation works is the same universe in which the wave function does not collapse but splits. That is not a coincidence. The anthropic principle and its weak and strong versions. This is a distinction that, when examined, speaks of a fundamental difference between observation and explanation. The weak anthropic principle is simply stated: the conditions observed in the universe must be compatible with the existence of observers. This is a tautology, but a useful one. It says that we should not be surprised to observe a universe fit for life, simply because in an unfit one we would not be there to observe it. That is what the hotel metaphor describes. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point. This version is far more controversial and is viewed by many physicists as teleological, implying a purpose, which is not a scientific concept. But there is an even stronger version proposed by physicist John Wheeler, the participatory anthropic principle. Wheeler argued that the very fact of the existence of observers is necessary for the existence of the universe. His argument is based on the interpretation of quantum mechanics. If observation physically changes reality, through collapse of the wave function or through choice of branch in the many worlds interpretation, then conscious observers are not passive spectators but active participants in creating a definite reality. This is where his phrase about the universe as a self-observing participant comes from. The idea remains highly controversial, but it raises a question that physics has not yet found a way to definitively close. Is consciousness an epiphenomenon of physical reality, or does it constitute it in some fundamental way? The problem of predictability in the multiverse and why it is the most serious scientific objection to the many worlds interpretation. This is an honest story about the real weaknesses of an otherwise attractive physical theory that cannot be glossed over. If all possible outcomes of a quantum event are realized in different branches, what exactly does quantum mechanics predict? Usually we say that quantum mechanics predicts probabilities. For example, the probability that an electron passes through the left slit is 50%. Those probabilities are confirmed experimentally with high precision. But in the many worlds interpretation, both outcomes are realized. So what is the meaning of probability? This is called the Born rule problem. The Born rule is the mathematical recipe for calculating probabilities from wave functions, proposed by Max Born in 1926. In the Copenhagen interpretation, it is simply postulated as a rule. In the many worlds interpretation, one needs to show that it emerges from the structure of the theory itself, not added from outside. David Deutsch and David Wallace have proposed a derivation of the Born rule from principles of decision theory. If you act rationally in a world where all branches are realized, you should weight outcomes according to the Born rule. That derivation is mathematically rigorous, but it relies on additional philosophical assumptions about rationality. Right now, this question remains open and is the subject of active discussion in the philosophy of physics. An honest acknowledgement of this complexity does not undermine the many worlds interpretation. It shows that real science is more complicated than popular accounts. Quantum biology and how quantum effects have already been discovered in living systems. This is a specific area of research that, when examined, speaks of quantum mechanics not being the exclusive prerogative of laboratory instruments, but permeating living nature far more deeply than is commonly thought. Photosynthesis, the process by which plants convert sunlight into chemical energy, was discovered in 2007 to use quantum coherence for energy transfer. The group of Graham Fleming at Berkeley published results showing that excitation energy is transferred through photosynthetic complexes with near 100% efficiency, significantly higher than would be possible by classical random walks. The mechanism is quantum superpositional walking of energy along many paths simultaneously, which find the optimal transmission route. This is not a metaphor. It was measured at room temperature in living biological systems. Bird navigation using the Earth's magnetic field is also thought to be based on quantum effects, specifically, quantum entanglement of radical pairs in cryptochrome molecules in birds' eyes. When a photon enters a bird's eye, it creates a pair of chemically active molecular fragments with entangled spins. The orientation of these spins relative to the Earth's magnetic field determines the chemical reaction, ultimately giving the bird directional information. Smell, too, may use quantum tunneling for recognizing molecular vibrations. That hypothesis remains debated but is partially supported experimentally. Enzymes, the molecular machines that accelerate biochemical reactions in our bodies, use quantum proton tunneling to increase reaction efficiency. Quantum biology is right now one of the fastest developing scientific fields, and it says that living beings do not simply obey quantum mechanics as a background law of nature. They actively use quantum effects to perform biological functions. Information as the fundamental substance of the universe. This is a conceptual story that, when examined, speaks of the deepest understanding of reality in modern physics, pointing to information, not matter or energy, as truly fundamental. John Wheeler formulated this as the aphorism "it from bit." His idea is that everything physical, every object, every field, space-time itself, is at its core informational. Physical reality emerges from the answers to yes-no questions, from bits of information. The wave function in quantum mechanics is a mathematical object describing information about a system. When a measurement occurs, the information about the system state becomes definite. In the many worlds interpretation, both branches carry complete information. Information is never destroyed, only becoming inaccessible from a specific branch. The principle of information conservation is one of the most fundamental constraints in physics. Classical physics does not explicitly postulate it but follows it through the reversibility of the laws of motion. Quantum mechanics explicitly postulates it through the unitarity of the wave function evolution. The famous dispute between Stephen Hawking and other physicists over the fate of information falling into a black hole, the so-called black hole information paradox, occupied physicists for several decades. Hawking initially suggested that information is irreversibly lost in black holes. He later changed his position. Right now, most physicists lean toward the view that information is not destroyed, but is somehow encoded in Hawking radiation leaving the black hole, though the exact mechanism remains an active area of research. If information is conserved, it means that the universe is, in a fundamental sense, a computational system that forgets nothing. Here is what, after an honest examination of everything we have considered, from the double-slit experiment to quantum computers, from decoherence to entanglement, from quantum biology to the no-cloning theorem, is the most accurate description of what physics says about the nature of reality right now. Quantum mechanics is the most accurate physical theory ever created. Its predictions have been confirmed to within 1 part in a billion in some experiments. It works. The devices that use its principles work. Quantum computers, lasers, transistors, MRI scanners, GPS systems whose accuracy requires relativistic corrections. All of this works precisely because quantum mechanics describes reality. And the mathematics of this theory, when read literally, the reading that Hugh Everett proposed in 1957, says that reality branches always unstoppably right now. The Copenhagen interpretation adds to the equations a collapse that the mathematics itself does not describe, as a way to preserve the uniqueness of our experience at the cost of an additional uncalibrated postulate. The many worlds interpretation does not do that. It takes the equations as they are. If the equations are correct, and they are correct because every working quantum computer is proof, then parallel worlds are real in the same sense that your keyboard is real. Hilbert space and why it is the mathematical container of all parallel realities simultaneously. This is a specific mathematical structure that, when examined, speaks of the multiverse not being a metaphysical addition to physics, but being built into the very formal mathematics of quantum theory. Hilbert space is an abstract mathematical space of infinite dimension in which quantum states live. Every possible state of a quantum system is a vector in this space. When a system is in superposition, its state vector is a sum of several basis vectors. In the many worlds interpretation, each of these basis vectors corresponds to a separate branch of reality. When decoherence occurs, the branches become orthogonal to each other. Orthogonality in the mathematical sense means they cannot interact, just as two perpendicular lines have no common direction. That is the mathematical justification for why you do not see the other branches. They are not hidden behind a physical wall. They are orthogonal to your branch in Hilbert space. That is why the radio station metaphor is so precise. A station at 99.5 MHz and a station at 100.3 MHz occupy the same physical space in your room, but they are orthogonal in frequency and do not mix. Parallel branches of reality occupy the same physical space, but are orthogonal in the quantum sense and do not interact. Quantum mechanics requires Hilbert space for its formulation. There is no version of quantum mechanics without it. And Hilbert space accommodates all branches simultaneously. Removing branches from physics means removing Hilbert space, and removing Hilbert space means removing quantum mechanics. Choose. quantum supremacy and what it specifically demonstrated in 2019. This is a turning point in the history of computing, which when examined speaks of a specific event after which the argument about using parallel realities for computation ceased to be purely theoretical. In October 2019, Google announced that its quantum processor Sycamore performed a calculation in 200 seconds that would have taken the best existing supercomputer about 10,000 years. IBM disputed this figure, suggesting that with certain optimizations a classical computer could manage in 2.5 days, still incomparably slower. The specific problem Sycamore solved is called random quantum circuit sampling. It is not a problem with immediate practical application, but it is an ideal benchmark to demonstrate that a quantum computer is doing something fundamentally different from a classical one. What exactly was Sycamore doing in those 200 seconds? It was holding 53 qubits in superposition simultaneously in 2 to the 53rd power states, about 9 quadrillion states at once. A classical processor would have to iterate through them sequentially. A quantum processor works with all of them simultaneously. Where does this parallel computation happen? David Deutsch answered that question unequivocally: in parallel versions of reality. That is where the computational resources are sufficient. In our single branch, they are not. 2 to the 53rd power parallel calculations require 2 to the 53rd power parallel physical systems. And that is exactly what the multiverse provides. Optimistic nihilism and how the physics of parallel worlds transforms the darkest philosophical worldview into something fundamentally different. This is a conceptual story that, when examined, speaks of a specific psychological consequence of accepting the physics of many worlds. Nihilism in its classical form is the belief that life has no objective meaning, that the universe is indifferent, and that we are accidental biological structures on an accidental planet around an accidental star. That is true. From the point of view of physics, we really are a byproduct of the universe's reproductive system, tuned to produce black holes, not humans. The universe was not created for us. That is not pessimism, it is accurate physics. But optimistic nihilism flips the conclusion from this fact. If the universe has no objective purpose for you, then it has no authority to pressure you. If the script is not written in advance, then you are the author. And in the context of the multiverse, this gains an extra level. The version of you that lived an ideal life exists in another branch. The version that suffered a crushing defeat also exists. The specific branch you are in right now is a unique point of view, the only place in the entire multiverse from which this exact configuration of experience is visible. No other branch sees the world through your specific memories, your specific connections, your specific scars. That is not a comfort invented to make you feel better. It is a consequence of physics. Every point of view in the multiverse is absolutely unique because the multiverse constantly branches, and no two branches have the same future from this point. Stars as nuclear furnaces and what that means for our connection to what happens at the quantum scale. This is a story that, when examined, speaks of a specific physical continuity between the subatomic and the cosmic scales. The carbon atoms in your body were created inside stars through nucleosynthesis, the fusion of light nuclei into heavier ones at temperatures of hundreds of millions of degrees Celsius. Quantum tunneling allows this fusion to happen. Without it, the Coulomb barrier between nuclei would be insurmountable even at those temperatures. The oxygen atoms in your breath are from stars. The iron atoms in your blood are from supernova explosions. The calcium in your bones is from stars. You are literally made of stardust that passed through quantum mechanical processes billions of years ago. And here is what follows from that in the context of the multiverse. If quantum processes in stars generate branching, and they do because quantum mechanics is a law of nature without exceptions, then every carbon atom in your body is the result of countless branchings that occurred over billions of years of nuclear reactions in stars. You are not just made of stardust, you are made of quantum branch stardust. The specific configuration of atoms that makes up you right now is one of an astronomically huge number of configurations existing in other branches, each containing a slightly different version of you with a slightly different history of the quantum events that occurred in the stars that created your atoms. Here is what, in the end, is the most accurate and most honest summary of everything we have considered, from the double-slit experiment conducted in 1927 to Google's quantum supremacy in 2019, from decoherence to Hilbert space, from the quantum biology of photosynthesis to China's 2,000-kilometer quantum network. Parallel worlds are not a metaphor, not an uncomfortable way of talking about probabilities, not an interpretational decoration on a mathematics that works without them. They are a direct, literal consequence of taking the equations of quantum mechanics as a description of reality, not just as a computational tool. The only reason most people do not accept this as an obvious fact is not the lack of evidence. The quantum computers that work using parallel computations are evidence. Quantum teleportation over 100 kilometers is evidence. Quantum coherence in living cells is evidence. The only reason is that accepting this requires radically rethinking what reality is, and that is uncomfortable. Physics is not required to be comfortable. And right now, sitting in a refrigerated chamber colder than outer space, a machine is reaching into other branches of reality and pulling out answers. The machine does not care whether you believe in parallel worlds. It runs. It returns correct answers. And the place where those answers come from is not inside this universe. The door is open. And the only honest thing to say is that we do not know what else might come through. We only know that the answers keep coming back. And that so far they have been correct. So far. If you made it this far, you have just stared into the deepest mystery of existence. Hit like, subscribe, and tell me in the comments. Do you feel like you are the only branch, or can you feel the others?